Hello, welcome to another Henstitute. Here we're going to look at a situation where we have moving fluid and we also have a difference in height. So water is flowing through a hose. So we're going to make the assumption if it's just plain old water that its density will be that 1,000 kilograms per cubic meter, so make sure that you don't forget that. It comes out of the tap at a pressure of 120 kilopascals. Now, we don't like kilopascals. Remember that kilo just means 1,000, so that's just 120,000 pascals. Velocity of 7 meters per second and height of 0. So in other words, it's flowing through this hose at a particular, wherever we're going to measure our kind of a reference height. It leaves the nozzle at a velocity of 4 meters per second and a height of 2 meters. What is the pressure of the water when it leaves the hose? So we have two situations here. It doesn't really matter which one we call what. So I'm just going to call this situation number 1, and we'll call these situation number 2. So the idea is we have water flowing through this hose. If I kind of imagine it here, it's flowing through this little section, and then it goes up to some other section, and the velocity actually goes slower. So the reason why what I know must be happening, even though they don't actually give me any numbers for this, is that it must be getting wider, because I know from the equation of continuity that a wider section is going to actually have a slower situation. So this is number 2 in our situation, and this is number 1. Doesn't actually matter which way we do it. If I flipped them, this problem will still work. But we've got the pressure down here, we've got the velocity. This is where it's going 7 meters per second, and then up here it's going 4 meters per second. And then our height, the idea is we're imagining kind of a dotted line here, and so this is our 0 point. And so when they measure the height, it's probably to the center of this tube, and this height is 2 meters. And what we're trying to do is figure out what is the pressure at this point. So we're trying to find P2. Again, just like I used to do with energy conservation, I did this back in the spring. Unfortunately, it was when we were doing some remote learning, so not everybody probably caught on right away, but for us, I went through it, is we write the entire equation. So this is our energy conservation. That's basically what Bernoulli's principle is. So P1 plus our 1/2 rho V1 squared plus our rho GH1 should equal P2 plus a 1/2 rho V2 squared plus rho GH2. And in essence, we're going to have numbers everywhere except for P2, and that's going to be our unknown. So P1, I'm going to leave this as, you have to change this into pascals. If you leave it in kilopascals, this will not work. So this needs to be written as 120,000 pascals. Now, the reason why it won't work is this part and this part, these other part, the rho, 1/2 rho V squared and the rho GH, those are actually written to pascals. They will solve for pascals. Now, I made a mistake. I didn't actually say this correctly. We don't actually have everything because H1 is 0, because our original height is 0. So I'm just going to add to this a 1/2 the density of my water, 1,000, times its velocity, which is 7 squared. And then over here, I've got P2. I don't know what P2 is, so I'm going to try to solve for it. A 1/2, 1,000. And this is now moving at 4 meters per second squared plus the 1,000 times 9.8 times 2. Probably the biggest thing I always get with these problems is people start seeing that there's density on both sides. They want to cancel all the densities. You can't do that unless you don't have a difference in pressure. If the pressures were the same, you could. So if this was coming from air here and it was leaving to air there, then we could say the pressures are the same, but that doesn't happen. In the notes I gave you, I talked about having like a container where you poke a hole at the bottom and water flows out, and then you had air pressure on top and air pressure at the bottom, and then it was the same, and you could actually cancel the fluid as long as you assumed that it was a non-viscous fluid. So now I can just take my handy dandy calculator and calculate some stuff. So I've got 1/2 times 1,000 times 7 squared. So this little section right here is 24,500. That's the pressure due to the moving fluid there. I'm going to add that to the 120,000. And I get 144,500 pascals on the left. P2 is what I'm trying to find. Then the stuff on the right here, so I've got 1/2 times 1,000 times 4 squared. So this little bit is 8,000. And then I have my 1,000 times 9.8 times 2. So this little bit is 19,600. So I'm going to add those two together. And I get 27,600. Then I can subtract that over to the other side to figure out P2. This is probably the most straightforward of my Bernoulli problems here. So I've got this 144,500 minus the 27,600, and I get 11,600 pascals. If I was looking for significant figures, it looks like everything's in 2, 2, 2, 2, 2, and actually I wouldn't probably even bother with the 0 because I don't deal with it. So if I was trying to round this to 2, this would be approximately 120,000 pascals. Then I kind of look at that answer. Does that seem like it makes sense? And sure enough, it does for two different reasons. As you go higher up in a fluid, you should actually have lower pressure. So I expect it to be smaller because of that. And then also, the faster you have a fluid moving, it should actually be lower pressure. And it did slow down a little bit, so the 4 meters per second was kind of counteracting that and trying to make it go back. So in essence, when I round this off, I actually get the same answer. So it's kind of like these two numbers almost canceled each other. Not perfect, because this is actually 116,900 pascals, but rounded to the same number of significant figures, you get the same answer. So it's kind of funny that it happened that way. Part of it has to do with the fact that this little piece was 24,500 and this little piece was 27,600, so they're almost the same. They almost kind of canceled each other. Hope you enjoyed this edition of the Henstitute, and this helps with some Bernoulli equation problems.